Welcome to Mr. Endress's Science Brainery, the only science brainery with, well, the name Brainery. In this video we're going to talk about matter, atoms, and molecules. Your teachers, or if you are a teacher, may know this better as MS-PS1-1, matter and its interactions, if your school or state has adopted the next generation science standards. If you are a teacher, I'll also direct you to my companion video to this. It's called MS-PS1-1 for Teachers. Among other things, I explain how I came up with my essential questions I'm going to answer here, and tell you how I might use this in my classroom, and also give you some sample assessment questions that you might see on your state test. So let's talk about matter, atoms, and molecules. We're going to begin with a phenomenon. So you may have heard your teacher say this, or if you are a teacher, you may have said this many times. Phenomenon is kind of the new buzzword in science. And what it really means is something that happens that leads us to ask questions about how or why it happened. Phenomena are the reason why science happens. Like, we know what we do in science, and we teach a lot of what happens in science, the things that we have discovered, but there's a reason why all that stuff happened. It's because somebody saw something and they did some experiments to find out why that thing is happening. So that's why you do an experiment. So a phenomenon doesn't have to be a big event or anything, like a supernova, or sometimes when we think of phenomenon, we think of the bright lights flashing or something. But that doesn't have to be a phenomenon. We're just going to simply look at a diamond and wonder, why is diamond so hard? Why is diamond shiny the way it is? Why do we spend all this money to buy diamonds? Because they're so beautiful, they're so shiny. Why are diamonds like that? So that's a phenomenon that we're going to try to investigate. To answer our question, we're going to look at a number of other questions about the structure of things and what things are made of, and that'll really get to the heart of this standard MS-PS1-1. And so this is going to be our map that we're going to use. It's kind of an outline of this, not only this video, but also of the lessons that will get us to our answer. And first we'll talk about matter and what is matter, especially what are atoms and what are elements. Well, atoms aren't the only thing that make up stuff. We're going to talk about chemical bonds. And after we get matter and chemical bonds, we can start looking at what makes up everything. We can start off, and we're going to do this in levels of complexity. So we'll start off with atoms that don't bond with other things. Then we'll move to atoms that bond with other atoms of the same type, so the same element. Then we'll move to atoms that bond with unlike elements. And finally, we're going to get to these very complex things where atoms will bond together, and they'll bond together in repeating patterns to make up what we call extended structures. And then finally, we'll get to what we'll say that is most complicated, and that is these extended structures, but they bond to form crystalline structures, or what are crystals is what we'll ask. And then when we find out what makes that crystalline structure, we'll know better what the characteristics of a diamond are, and we'll be able to answer our questions. So, here we go. Our first question is, what is matter? And so I'm going to give you a big science word here so you can impress all of your friends. What is matter? Matter is stuff. Matter is made of stuff. Things like desks and pens and trees and air. All of these things have stuff. And how do I know air is made of stuff? Well, because I can stuff it into a balloon. Okay, so it's made of all this stuff. Now don't get confused, not everything's made of stuff. Energy's not made of stuff. Your thoughts aren't made of stuff. Well, what is matter? What is matter made of? Matter is made of atoms. We can't see them, they're far too small to see, but if you look at your hand very, very closely, well, you'll just look like an idiot because they're too small for you to see in your hand. A regular microscope can't even see them. A regular microscope might magnify things by 100 times or maybe even 1,000 times, and that's far too small. We need something that's going to magnify it by 1 billion times. Recently, scientists have developed microscopes that can take images of atoms. So here's an image. This is the first image of an atom. This is a hydrogen atom. It's not quite a photograph, but an image that's as close to a photograph as we got at the time. However, this is interesting. In 2018, a student at the University of Oxford was able to pin down a single atom using electric fields. Everything in the world that is stuff or matter is made of very small building blocks called atoms. Now that we know what atoms are, what's an element? Well, an element is a particular type of atom as distinct from all other types of atoms. That's my definition. If you don't find it very useful, here's an example. Let's think of atoms as Legos. If you think of all the stuff around you, again, this pen or pencil or book or even air, as like a house, and that house is made of smaller building blocks called the atoms. In this case, it's called Legos. Each little piece would be the atom. So what you could do is you could take it all apart and you could put the blues over here and the greens over here and the reds over here, and you could divide them with the reds that have 6 on them, the reds that have 8s, the yellows that have 4s. So, and then you have all these different blocks, and they're Legos. They're still the smallest building block, but they're all distinct from one another. And so each one of those little piles would be the elements. Each one of those piles is made of atoms, and each of those are slightly different than each other. Each different block represents a different type of atom, and those are elements. So look at that definition again, and it might make a lot more sense. An element is a particular type of atom as distinct from all other types of atoms. How many different types of atoms or elements are there? Scientists have found about 118 different types of elements, and they placed them on this neat little thing called the periodic table of elements. So if you've ever wondered about what that thing is, that's what that is. That's all the atoms or different types of elements that we know of. However, you'll probably never come in contact with all the different types of elements. In fact, in your life, you'll probably only actually come into contact with about 30 or 40 of them. In fact, your body's mostly made of only 4 different elements: carbon, hydrogen, oxygen, and nitrogen. And these, by the way, are gases. So all the stuff in the world, all the matter, must be made out of stuff more than just atoms. So if you're made of all these different gases in your body, only 4 of them, then there must be something different. There must be something there that makes them all different that they can make your body. So our second question is, what are atomic bonds? Well, atomic bonds are energy bonds that hold some atoms together to make molecules. Okay, so there are 2 things that need to be explained there to understand that definition. First,
some things are made of just atoms that don't bond together, and some things like water are made of atoms that are held together by bonds.
And what holds them together is a type of stored potential energy called chemical energy. For our current purposes, it's necessary to remember that and what holds them together is a type of stored potential energy called chemical energy. For our purposes, it's not really necessary to remember that, but those will come into play more when we start talking about chemical reactions. What is important for us to remember right now is that atoms can take on different chemical properties depending on how they're bonded together. For example, oxygen. Oxygen, when you have an O2 molecule, so this is O2 because there's 2 oxygens. This is the stuff you breathe. You breathe the molecules bonded together. This right here, when it's added another oxygen to it, now it turns into O3, and this is something different. And the reason it's different is because it has more bonds, more chemical bonds holding those oxygens together. So, what's a molecule? Molecules are 2 or more atoms bonded together. So, every time that you see that they have this bond holding 2 atoms together, that's a molecule. So everything around us is made of 2 things: matter, atoms and elements, and energy, chemical bonds which sometimes hold these things together. We're almost equipped to look at the varying complexity in things, but first we need to introduce models. So our next question is, what is a model? Well, we're getting into how to do science, because scientists use models. Models are an essential scientific tool used to represent some part of the natural world. They're usually mostly for things that are either too big or too small or too complex to study without some kind of representation. A good model has what we call descriptive power, and that basically means that it can describe. It's very good at describing what it's trying to describe. We will obviously be limited to models when talking about atoms because they're way too small for us to see. So with this in mind, let's look at some atomic structures, starting with the most basic, which is an inert atom, or we might call it a noble gas, sometimes what they're called. So question 4 is, how can we make a model of inert atoms? We call these inert gases or a noble gas since they're all gases. An inert atom is an atom that does not bond with other atoms. Helium is this type of atom. The chemical symbol for helium is He. So I could simply draw a model of a helium atom like this. Just put He in it. And that's one atom floating around, not bonding with anything. If I drew something like a helium balloon maybe, the helium balloon would be filled up with He atoms, and I'm not going to draw a bond between them because they're not molecules, they're inert atoms. There are 6 inert gases in all, and you don't need to remember this, but they're found in group 18 on the periodic table of elements. So those are all of our noble gases. Let's get a little more complex and move into question 5. Question 5, how can we make a model of a molecule made of only one type of atom? Or remember, the type of atom is called an element. So how can we make a model of a molecule made of just one kind of element? Well, first, let me remind you of the term molecule. Remember, a molecule is 2 or more atoms bonded together. So anything I draw here, anything that I'm trying to represent here, can't be 2 things that unless they're bonded together. They have to have that bond in between them. A good element to look at is, like we looked at earlier, oxygen. Oxygen bonds with itself to make this O2. Okay, remember that was just 2 things bonded together. And if you ever really wonder what those numbers mean, that's what that number means, O2. So here are 2 different substances. This one right here is the oxygen that we breathe. This one right here is the ozone that's like found in the ozone layer. So you see here, the big difference is that you can't breathe this one, but you can breathe in this one. Your body needs this. There are other differences too. This one is clear, it's transparent. This one has kind of a blue tint to it. This one doesn't have a smell. If it does, that's not oxygen you're breathing. And this one does kind of have a pungent odor to it. And this is what causes those differences, and that's that bond in between them. The bond changes its physical properties. So here's another model of O2. Notice that I can't use these 2 tennis balls because I have to have the bond in between them. Other gases also bond with themselves. Nitrogen's found in the atmosphere, and it bonds with itself. H2, hydrogen, bonds with itself. This, by the way, is used for fuel in space shuttles. The way that we do that is we pump it up with liquid hydrogen, which is H2, and chemically break this bond. And I told you that bond's made of energy, so it releases an awful lot of energy when you break that bond. So here we go. Let's get a little more complex, and we're going to go to question 6. Question 6. How can we make a model of a molecule made of different types of atoms? Or, again, different elements? Well, here's a classic example, and that's water. Water is H2O. Remember that 2 means there's 2 H's, so H2O. And that's a water molecule. I could also draw it like this. That would be a water molecule. And it doesn't really matter where I'm drawing these bonds. I mean, it will when you really start talking about chemistry and wondering how the chemical reactions happen. But for our purposes, I could easily just draw it like this if I wanted to. That's a water molecule, or Mickey Mouse. So those are water. That's a water molecule, H2O. Here's my real life model. Here's my oxygen and my 2 hydrogens. So a guy walks into a bar, and he goes up to the bartender. Yeah, I switched topics right there into a joke. And he walks up to the bartender and he says, Whew, hey fella, how about getting me some H2O? And the guy at the bar looks up at him and he says, yeah, bartender, get me some H2O too. So the bartender brings them both their drinks. The first one chugs it and has a refreshing drink, and the second one chugs it, he dies. Okay, because it was H2O2. That's hydrogen peroxide. It's not really going to kill you, but the joke wouldn't be nearly as funny. So here's why that happens. Let me show you something interesting. H2O is water, but if I add another bond to it, H2O2, so I add another oxygen atom and I bond it together, I have H2O2, two hydrogens, two oxygens, and I bond them together, I get something completely different. I got hydrogen peroxide. So this is the stuff that you put on sores and it bubbles up. And all I did was change the bonds and added another oxygen. So I have the same elements there, but I changed the bonds, and now I've changed the whole atomic structure. I mean the whole physical properties. Ammonia is a substance that's used for a wide variety of things. For one thing, it can absorb a lot of heat, so it's often used in refrigerants. And ammonia is one nitrogen atom and three hydrogens. And so you probably can figure out the chemical formula. It's going to be one nitrogen. It doesn't get a little subscript because it only has one N, and three hydrogens. So it's NH3. That's how we write it, and that's how we draw it. Here's my model that I've made of it. See, I have my N and I have three H's here. So this is a model of ammonia. Finally, another one I want to show you is carbon dioxide. Carbon dioxide, one carbon, dioxide, that's where we get di, two oxygens. So we have carbon and two oxygens. Carbon dioxide. So remember, I could draw that like this. I could draw it like this. So I have a lot of different ways that I could make this model of carbon dioxide. Carbon dioxide, I could also show you something like this. So that's carbon dioxide. Here's my carbon, here's my two oxygens. Now carbon dioxide is a molecule that floats around in our atmosphere. We breathe it out. It might have come from burning wood, or it might have come from fossil fuels burning or something. But this is floating around our atmosphere. And what's interesting is these molecules float around and they're not attracted to one another. And so what happens if we have some molecules and they are attracted to one another and they start sticking together? Well, now we're getting a little more complex. So let's go to question number 7. Question number 7. How can we make a model of an extended structure made of repeating subunits? So, some things we said are made of, like helium, my helium atom, and helium doesn't bond with anything, so it's an inert gas. And some are made of molecules, like carbon dioxide. So here's my carbon dioxide, two oxygens, dioxide. And this would be like a helium atom and a carbon dioxide molecule, and they don't bond with themselves, so they just float around freely. So some things do, like some things are made of single atoms, like carbon, made of just one atom, carbon, and some things are made of more than one atom, like water, and they're actually attracted to one another. And what happens, well, when this happens? Well, what can happen is that they can just start, all the molecules will start sticking together and make one long molecule called an extended structure. So let's look at a couple examples. First, let's look at nylon. Nylon is made of subunits, but on a macro level, which means when we're looking at nylon, we make it's kind of like a thread. We make rope out of it. We can also look at like a watch band or something we might make out of nylon, but mostly it's ropes. And if you look at the tip of this nylon, it's like it's braided together, and there's a very good reason for that, and it actually occurs on the molecular level. Well, here's a single molecule of nylon. See that O, C, and N, and they're all combined, and it just kind of, that's the single molecule. Well, those molecules join together and keep doing this over and over and over again. See, here's one of the subunits, and then here it starts again, here's a subunit, and here it starts again, here's a subunit. and they make these long strands, and those strands wrap around each other and they braid together, kind of like it does on the macro level. So that's why nylon looks like that. Your hair and your fingernails do the same thing, by the way. Let's look at glass. A single glass molecule is made of one silicone atom and two oxygen atoms. The chemical symbol for silicone is Si. So if you have been keeping up with chemical formulas, you can probably guess the chemical formula is SiO2. So one Si atom and two O's. But these molecules are attracted to one another, unlike something like carbon dioxide, and glass actually looks something like this. Here's the silicone atom, and here is, and here's one, and here's one, and these are just subunits of what we call them. So this is the whole silicon dioxide atom right here, and this is just a subunit, and it repeats itself. See, it's repeating itself over and over again because they're attracted to one another. And so the silicon dioxide is attracted to one another. So we can call this an extended structure made of repeating subunits. And these subunits, in this case, are the silicon dioxide. And so we'll get to question number 8. Question 8 is, how can we make a model of a crystal? Now, a crystal is not what you might be thinking. When we say crystal in real life, we're talking usually about shiny jewelry or a priceless chandelier or something like that. But that's not really the case in science. In fact, most solids are crystals. Wood is even a crystal. So we need to ask, what is a crystal? Now, this is my definition, but I think it's good enough for our purposes. A crystal or a crystalline structure is an orderly arrangement of atoms or molecules which repeat themselves in a three-dimensional symmetrical structure. Now, what does that mean? That's a lot to take in, so let's break it down just a little. First, we are still dealing with repeating subunits and extended structures. So we're still dealing with molecules that are, unlike carbon dioxide, attracted to one another. And the molecules keep repeating themselves. But we have this added three-dimensional structure. And to me, it's a lot easier for me just to kind of show you that, the symmetry in this. So if you look at quartz here, see how if you cut it down the middle, and no matter how you cut it, it's in a symmetry. Every side is going to look the same. And you have another one that's tied together, and it ties together again right here. So those are three-dimensional structures. Well, here's the water crystal, and see how it's shaped. But if you look at it from the side view, it has this three-dimensional structure. All these bonds are holding it together, and it has kind of this perfect symmetry. Graphite. If you look at graphite, that's what's in your pencils, by the way. You don't have lead in your pencils. We often say pencil lead, but it's not really lead, it's graphite. And so the graphite right here, you can see how it's very structured, and if you look at it from its side, it has this three-dimensional layered structure, has symmetry. Let's look at salt, and we're going to make a salt crystal. So if you want to, you can actually draw this with me. We're going to start off with the chlorine and sodium. That's what makes up salt. This is going to be our sodium is the blue, and our chlorine is going to be the green. And this is a molecule. So if you've been keeping up with it, then they're bonded together. So we want to draw a bond in there. And it's an extended structure, and this is just a subunit. So we're going to need to draw another one. And we're going to need to bond those together because the subunits are attracted to one another. Well, we need to draw it again. And we're going to bond them, and we're going to bond them together. So there's our small crystal of salt, and we can draw another one, another subunit. I'm drawing these are sodium chloride molecules, and they're all bonding together because they're sticking together. And so I'm drawing this three-dimensional shape right here. And now I have my crystal structure. The last crystal I want to look at will really help us get to the answer of our question. Remember, our phenomenon that we're looking for the answer to is what is diamond? Why is it so hard? Why is it so shiny? So the last one I want to look at is quartz. Quartz is a mineral. It looks like this. It looks just like a rock, and you know it from you might have seen this in sand, like the little glass-looking pieces in sand. That's quartz. Quartz is also SiOU. So it's also a silicon dioxide molecule. But it's going to be different than glass. So remember, this is what glass was made of. But now with quartz, we get this three-dimensional symmetrical structure. And so quartz and glass are made of the same thing, SiO2, the same kind of molecule, but they're structured differently. Remember, substances can have different physical properties, even if they're made of the same atoms or the same molecules, if they're just bonded together differently. And in quartz, that's what's happening. They're bonded together in this three-dimensional crystal. Quartz looks like this on an atomic level. Well, let's compare glass and quartz. They're both made of the same molecule, and both of them, the molecules repeat themselves over and over again, so they're both extended structures. However, glass shatters when you hit it, if you've ever noticed that. And quartz is very, very hard. Well, why is that? It's because of this crystal lattice, this crystal structure that all the bonds are holding it in place three-dimensionally. Okay, with that information, let's move on to a diamond. I think we have everything we need behind us to answer our question, what makes a diamond so hard? Well, here's a diamond subunit. All those are carbon, by the way. Diamond's made of only one element, and the carbon is bonded together into this three-dimensional symmetric shape. That's why it's so hard, because of the crystal structure. In fact, because of the way carbon is on the atomic level, it actually makes more bonds than other things, than like, say, quartz, and so it's being held together very firmly in the middle here by all these bonds going every different way, and very symmetrical bonds holding it in place. So that's why diamond is very hard. Well, what about shiny, though? Why is it shiny? Diamonds actually aren't shiny. Diamonds actually just reflect light, or they're transparent and let the light go through them at different angles. And diamonds have to be cut just right in order for you to get this shine out of them. That's why some diamonds are cheap and some diamonds are actually more expensive. If you're ever going to pick out a diamond for somebody, you tend to know a lot about diamonds. In fact, the saying is that men know a lot more about diamonds than women do, because generally men buy the diamonds, and so they have to actually study them and figure out what makes a diamond great. So I can tell you from my experience, diamonds have to be cut just right, and they have to be pure so that the light will shine, will hit them and make it illuminate. Well, why does that happen? That happens because you can cut them along these edges. So they're very, very hard here in the center, but they have this edge right here that can be cut. So when you're cutting into a diamond, when you cut a diamond, you're actually cutting along the edge of where all these atoms are. So it's very strong here in the middle, and it's weak right here where you can cut along the edge and make it very shiny. So there you have it. In this video we walked through what things are made of, what matter is, and atomic bonds, and then we're talking about these simple substances like inert gases, and moved to atoms that bond with other atoms of the same element, and then we moved to atoms that bond with different elements, and on to extended structures, and then we talked about even the most complex of how those structures can come together into a three-dimensional shape that's very, very hard, and we call that a crystalline structure. And that's really all there is to this standard right here of MS-PS1-1, knowing the complexity of all these different things and making models of each. I hope this video helped. Again, for teachers, I hope you check out the companion video for this, MS-PS1-1 for teachers. You can also check out my store on Teachers Pay Teachers. There I have some reading selections that go along with this, as well as some worksheets and a test that I give on covering the material in this video.